Right. Oh, morning, everyone. Okay. See if this works. Right. Somewhere in the new Concrete Hard Standing Handbook is a little dark corner, and there's a paragraph that Matt Boller and I slotted in based on the back of ACPA webinars and the 2022 International Conference. And we were looking at alternatives to the RR87 model, which frankly is a bit past it, but it's all we've got really in the UK. So, and one of the things we unearthed was this thing called Optipave. So, Optipave is the name of the model. TC Pavements are the folks that developed it and sort of deploy it. And the commercial interests were brought out by a US fibre supplier called Forta. And since this paragraph was slotted in, I've been in touch with TC Pavements. They're based in Chile, so nice and local. So it's the communication's interesting, but it does work. And their MD actually did his degree in University of Birmingham, so it's culturally it's closer than you think. So anyway, we've been taking this forward a little bit. It's all a bit informal and early days, but I just want to say just expand a bit on this paragraph and saying what I'm doing with it, which at the moment isn't a great deal, but it's interesting. And I'm going to, hopefully nobody's got to the end of that paragraph, because there is a typo in it I spotted when I was putting it together.
Move on, Jack.
Yes. I'll let you know afterwards, Steve. So what it says at its most basic is actually, oh, there's a monitor here, fantastic. The whole sort of premise of the whole thing is normally what we always do is we work out our design thickness, design slab thickness, and then we divide it up into joints. We do the jointing strategy separate afterwards. But what this says is actually thickness and slab size are actually related. And that's what those curves on the left-hand side are saying. I think that's output from AASHTO-Ware, which I'll say a little bit about in a minute. But any structural engineers in the audience will know, what is it? Is it WL/4? Someone will correct me. So we know intrinsically that shorter slabs are stronger than large ones. Obviously, block paving there is kind of the ultimate short slab. 200 by 100, and we stick 100-ton reach stacker wheel loads on it. I thought the Lego effect might be a bit more poetic than WL/4, because we all know as small children that the small tiles are a lot harder to bend than the large ones. And anyway, some clever folks have come along and related that to concrete paving. So this started out as a curling in parts of South America is a massive problem, and from photos I've seen, compared to what we get, it's bonkers. It's very, very fast, and it's very, very severe. So the folks down there were having issues with it, and what you realise quite early on is if you've got large slabs, the quickest way to sort it out is just saw them up. And there's a little diagram there on the left. If you saw a curled slab in half, you reduce the curl by 80%. Now, I haven't done the maths, but I'll take that on trust, and maybe someone can do the proof over lunch for me. So this is going back a few decades now, and it triggered all sorts of things. So I think in no particular order, there's this AASHTO 98, and you'll think, oh, Bully's made another typo, but it's not AASHTO 93. There is an AASHTO 98, I think it was short-lived, that took some of this curling problem on board. Then there's also a study in the United States. There was a section of Interstate 30 in Illinois where a concrete section failed, and it turned out that the design had been completely in accordance with standard, but it had failed because of curl. And that sort of got a few heads together, and there was a lot of work done at University of Illinois. I can't tell you the whole story due to lack of time, but basically the people that were involved with this are like concrete pavement demigods. They're you know, you get them to, you know, if you meet them, you get them to bless your kids, really. It's not, they're sort of, you know, forgotten more than I'll ever know anyway. And out of that came this thing called Optipave, and what it says is, really it's in response to curl. Now in the States and the Americas, they're obsessed by it now because of what's happened. And in essence, what it says is the shorter you make your slabs, short enough so there's only one axle on the slab at a time, you mitigate the corner and the massive corner and edge breaks you'd get with curling, and you can also thin the slabs down. You can see there in the diagram on the right, if you've got a large slab and you traffic it with a multi-axle vehicle, it's just like a giant upside down 3-point bending test. So the shorter slabs are inherently stronger. And as I say, some very clever people have actually captured that into some design theory. You could, certainly TC will argue this, that it's actually an extension of the AASHTO, Mechanistic Empirical Pavement Design Guide, which is a bit of a mouthful. Now, I haven't driven that software. It's about, last time I looked, it's about $7,000 US, so it's a bit hard to justify unless you're using it all the time. So again, I have to take this on trust, but it does. It's one way of thinking of it is an extension to some very respectable software. This MEPDG is an extension. Obviously, AASHTO 93 is now gone, and they use this instead. And it's a lot more computationally heavy. You have to almost track your elastic modulus deterioration on a monthly basis. Very computationally heavy, and as I say, I know just a little bit from scratching the surface, but I'm no expert on it. So moving on, you've got ACI 330, which is kind of the equivalent of our Concrete Outstanding Handbook, and Optipave is recognised in there. There's a section on it. But what's really interesting is typical Optipave design. We're using, 1.75 joint spacing, joints are sawn, no dowels, no sealant, and they use synthetic fibres quite a lot, and I'll come on to that in a minute. So it's, it's a lot neater design. I've got one case study, and the reason I chose this one is, hopefully you can see on the screen there, you can see the saw cuts with the short slabs. There's a shoulder on it as well. You can also see that there's no joint seals going off infinity. I don't know whereabouts in Chile this is. I just picked it because it was the best looking photo. But they have done, roads across, in desert climates without any blow-ups. But this one is, you can see there, it's been down for almost 20 years. Okay, 8 MSA, it's nothing like we deal with on the network, but it's rural road. That was maybe in the days a little bit conservative with the 170, but I'll show some more figures in a minute. It's a bit like AASHTO in the way it works. You put in a reliability and you set targets for percentage cracking, percentage faulting. And if you want IRI, which is International Roughness Index, again, it's not a model we use much in the UK, so I confess to not being an expert on it, but you do rub up against it from time to time. And you can see there that the point of this, one of the points of this slide is that when they came back and evaluated it 8 years after construction, it was performing better than the model predicted. So probably the reason we haven't heard of it much is, of course, these are the completed projects. There's a lot of them. You can see they're concentrated in, obviously, Chile and working outwards. There's certainly, quite a lot of interest in the States. I know there's folks in Canada I'm in touch with that are starting to pick it up. And there is and if you go on sort of OptiPave webinars, there's all these engineers from like Ecuador and Costa Rica and all these exotic places. So there's quite a bit of there's a bit of interest overseas. You can see we've got the Botswana job. I think I'm told was done this year, and TC were well chuffed that they managed to get that one done. A little bit there in southern Europe. You've got one in France, but obviously there's a big blank in the UK. It's not been, at least to my knowledge, it's not been used yet. But with a bit of luck, we might try and do something about that. And you can see there in the key that it's not just it's sort of industrial sites, some car parks. It's not just highway work. Interesting comment that certainly in parts of South America, that OptiPave was actually taking market share from asphalt. I'll say that again because it sounds really good at a BritPave conference. OptiPave is taking market share from asphalt. Yeah. Anyway, quick. This is a quick explanation. So there's a lot of. I don't know if it's a true HVS, heavy vehicle simulator, but if someone no doubt will tell me I've called it by the wrong thing, and never mind. Apologies for that. But the point is the photos on the right. So the one in the middle there, that's that's a plain concrete slab. But if you start putting macrosynthetic fibres in, it's bomb-proof. It really toughens really toughens up the slab. So that's. As I said before, that's used quite, pretty frequently. You can do unreinforced, but for long design life, then macrosynthetic fibres is a good idea. Which is why a macrosynthetic supplier has got the commercial rights to this. It's all enlightened self-interest. Slight digression on fibre reinforcement, because I think as consultants we have a bit of a. It's a little bit of a challenge for us to work out what dose we should put in, unless you're using the Interpave model, because it just says, well, if you want a certain materials equivalence factor, you put this dose in. But of course, it only deals with steel fibre. I was a little bit, and at the time we did the Concrete Art Standing Handbook. It was macrosynthetic fibres was a bit of a black art. You tend to have to rely on suppliers' black boxes, which if you're a consultant is a bit of a challenge, because you supply me 20 grand's worth of synthetic fibre, I still want £10 million liability out of you if it goes wrong, and it's a little bit of a challenge to sort out commercially. But what I'm finding, and it's not really it's not quite pavement related, but we've done a couple of track slab and structural jobs where this problem's come out. So you can see on the left there, that's actually some real data. I can't say where it is, but it's not in the UK. And you've got a sort of 5 kilograms of synthetic fibre, and you get the normal sort of beam test response there with a peak and the strain and the sort of residual strength there. But if you really dose it up, you get this strain hardening effect, which you can see in the bottom left diagram, and that's what the designer wanted. But when you start, what they found on site is when you start beefing up the fibre dose to that sort of level, it causes all sorts of challenges with workability and finishability, and so the client's getting something that doesn't quite look as good as he thought. So it's raised one or two eyebrows. It's nothing, nothing sort of massively serious. It's just annoying. But you're in this quandary of do you try and pare down the fibre dose, or go the full self-compacting concrete route, which is it's not great for carbon because there's a lot of powder in it. So the question I've got is that realistic? And I was when I was speaking to TC Pavements, that diagram on the bottom right, they put that in a presentation they did for me, and I thought, oh, that's interesting. I used that very diagram in a report only the week before. So it triggered a conversation. What that is, it's University of Illinois again, and what they've done is that's fibre reinforced concrete, but not in our two-dimensional European standard bending test, but they actually tested slabs. And you can see there it's all, lovely strain hardening material when you put fibres in it. And so what that suggests is there's actually a specimen size effect when you're looking at the fibres. And of course the comment from TC Pavements was of course real pavements don't have notches cut in the bottom when you do the beam test. So I know why they obviously understand why they put the notch in there. You want to promote a crack, but there's a sort of argument that it might be distorting the behaviour. So there's these specimen size effects and distortions in the evaluation. So relating that back to the diagrams on the left, the question is, are we putting more fibre in than we need to satisfy these tests? Or for a bit of research, and if anyone's got research budget, we'll bite your hand off, to maybe look into that a bit deeper and try and get out of this sort of commercial conundrum that we have as consultants. So it's early days with that. So I just wanted to look at a few jobs where I've started playing with this, and this is one of them. That picture there is from Hinckley C. I'm afraid I've stolen it off the web, but I'm sure Electrical Review is a fantastic publication. I strongly recommend you read it. But it's not, obviously they've got there's all sorts of photos kicking around with these new types of towers, but of course you can see there the real work of art is that Hall Road, and because I was part of the design team for it. Traditional geogrid reinforced unsurfaced, which is pretty much what you'd normally do for those sorts of jobs. It's down for about 3 or 4 years and then gets taken up again and the land gets restored. But you can see there's some pretty hefty plant needed to install these towers. The point about Hinckley is there's loads of really bouting quarries right next to the job, so getting stone to site is easy. But the jobs we're looking at now are on the other side of the country, where there are not massive aggregate supplies, and there are challenges with transporting large quantities of aggregate on very minor roads through little villages, on the local network, and over long distances. So the question's been asked: can we reduce, if we go for a surface road, can we reduce the volume of material that we're bringing in? And it's been done with OptiPave. They've done it overseas, where they've done literally just put an OptiPave solution straight on the ground, so no foundation, and you can customise your analysis to allow for that. It's fairly straightforward. So started doing a bit of optioneering for a couple of jobs and started looking at this. So I can't say where this job is or what it's for. It's still pretty much live, but we did it's less than 0.5 MSA over a 3-year life. So it's not exactly highway loading, but it's when it does get loaded, it gets pounded. I put in C4050 concrete, beef up the flexural strength, and we don't have to air entrain the concrete, save a bit of carbon. And no funny stuff, no reinforcement, no dowels. Although you'd need dowels at day joints, but otherwise it's undoweled. And no curbs. 80% reliability. If you know your AASHTO 93, that's for minor roads, that's perfectly reasonable. 20% cracked slabs and 5mm allowable faulting. And you put that in. We were looking at different CBRs. I think with the geology they've got, it will probably be. I'm confident that sizable stretches of this will actually be above 9% CBR, but we were asked to look at what could possibly go wrong. And you can see there we're getting very, if you I'm not sure, well, if you use the Concrete Hard Standing Handbook, the minimum traffic class is T1, which is 5 MSA, and you'd be up in probably just south of 200 mil. So there's a sizable saving in slab thickness there without any fancy foundations. I've actually rerun those calculations yesterday afternoon, and you could actually knock about 5 mil off that. I found a little mistake in the calculation, so sorry about that. And the other thing that's sort of preoccupying a bit of my time at the moment is cycle tracks. And you can see there, it's clear, you're getting this sort of longitudinal cracking, and there's whole jobs in certain parts of the country where this is rife, including a national highways jobs, because I was looking at one only last week. Not as bad as this, but you're getting it, and it's again it's a sort of at least part of it is climate change. You've got shrinkable clay and very hot weather, and a lot of this stuff. Certainly, some of the jobs I'm looking at, it's a sort of thing that comes up used to come up every 4 or 5 years. You'd get asked to look at one, and then in 2022 there was about 5 all kicked off at once. So it's sort of combination of climate and shrinkable clay. So what I started to do is have a look at the tables on the right there are straight out of the current DMRB. They have different standards for footways and cycle tracks, depending on whether you've got light or heavy vehicle overrun. Light vehicle, I think, is one vehicle a week, and the heavy vehicle overrun is something like 1 vehicle a day. The one in the picture is, from what I've seen of it, it's just dog walkers and joggers using it, so we're well below that. So that's not, as far as I'm concerned, that's not traffic damage. So I thought it'd be interesting to just see what an OptiPave design would do, and that's the diagram at the bottom. So again, 80% reliability. I pared the faulting right down to 2 mil because we don't want a trip hazard on an amenity pavement, but it's actually the cracking that governs it. I put 150 type 1 regardless because it's just a nice minimum for normal earthworks plant. No curbs, no dowels, unreinforced. And you can see there you're getting a substantial reduction compared to the DMRB, especially if you're you're into the heavy vehicle overrun. So it's just a little exercise. I've used different stiffnesses. You can see it's DMRB is kind of the odd one out because your bound layer thickness is always constant regardless of the foundation. That's the way they consider them separately, but in a lot of models it's not like that. Interpave's another one. Something you have to watch when you're doing your subgrade assessment, but you can see there's a little bit of variation there. So I thought that was interesting. Be nice to trial it. And the other thing that came up, anyone that was here 2 years ago will remember the Keacrete permeable paving, and I can take no credit for this other than to say that I got Keacrete, Imperial College and TC in a room together, and I said, you guys need to talk. And the reason for that is that the issue with Keacrete, certainly 2 or 3 years ago, I think it's resolving itself now, but was trying to get in a sort of workable thickness to form the holes, but there were sort of practical limits on the thickness, and it was a bit of a chat. If you use your DMRB and Westergaard and those sort of models, it's giving you a thickness, that's not really comfortable with the practical limits on forming these holes. I would say, incidentally, that I've seen the research they've done on the hydraulics for this, and it's really meticulous. But there's a bit of work going on to try and get it beyond the hydraulics, out of the lab, and to try and get some to try and actually build something out of it. So there's some testing. I think it's just starting now, but there was a suggestion that, with a little bit of extra testing, you can get some parameters and then calibrate your OptiPave model, which brings your thickness down, and this suddenly building this in situ becomes quite a bit easier. So it's early days yet, but hopefully we're on the way to a workable system. I take no credit for this except to just get these two folks in a room talking, but we'll see. Hopefully I'll be a bit more to report next year. So that's all I've got to say, thank you. Special thanks to Juan Pablo and Dr. Kia. I'm piggybacking on their life's work, which is a huge responsibility, and frankly that's a bit more of a worry than any questions you guys might have.
Thank you, Jack. Thank you very much indeed. Any questions?
Oh, God, it would be Adrian, wouldn't it?
Plastic fibres.
Yep.
They have different thermal behaviour. So when temperature changes, I'm not sold that they have the same strength in interaction with concrete. Do you have a view on that?
I don't. The way TC seem to approach it, and I'm putting words into their mouth which might be unreasonable, it just comes from putting this stuff down and observing what happens. Now they've done roads with this stuff in desert conditions quite happily. So I suspect the answer to that it's not a problem really. Now is that because of the short slab or because of the property of the fibres? I couldn't say.
Sorry, probably to answer, if the temperature range stays similar, I don't think there's an issue. But if the temperature range varies from 0, let's say, up to 35 degrees, you wonder whether there's a weakening in the interaction.
Yes.
When you load
All
it.
I can tell you is that climate data is part of the model because it's it's aimed at the United States, and of course, winters in Michigan or Wisconsin are quite different from summers in Florida and Texas. So they have a huge range of climates that we don't. So it is allowed for. I can't say how it works under the bonnet and whether that's taken into account, but it is something that's thought about. I'll try and get you an answer informally. You'd expect nothing less from me.
Any other questions, please? Can you whiz over there, please, Beverly? Thank you.
I just wanted to know if you had any knowledge of the costs, Jack, especially kind of in comparison to a standard.
I don't. I've not got that far yet, but you can. It's not a big job to do the sums. I'm on leave next week, so maybe I'll do that exercise for you if you ask nicely. But it's not the hardest thing in the world. But
do you think that's a barrier to implementation, or
I don't think cost is, because you're using we can use we're getting thinner slabs and we can customise our foundations. There isn't anything that says thou shalt use type 1, and it wasn't in my presentation, but I did another job. Looked at another job where we just took Site 1 gravel from a borrow pit rather than bringing loads of aggregate in by rail. There were sands and gravels on site that were, I think it was borderline type 2 sub-base standard, and we can customise the model based on that. So saves a bit of money. So you've got that extra customisation if you want it, completely non-standard, but you can do it.
Anyone? Any more? No. Jack, thank you very much indeed.
Always a pleasure, Steve.
Just to let you know, we're not going to be organising a study trip to Chile. It's not in this year's budget, I'm afraid.